What do the 7 bridges of Königsberg and this odd-looking robot I built as part of my PhD have in common? Well, they both have a connection to a mathematical framework called graph theory. The residents of Königsberg have a question. Is it possible to find a route that crosses each of their 7 bridges exactly once? This question caught the attention of a famous mathematician named Euler. He made an important realization. It really doesn't matter what path you take when you're not on a bridge. So we can represent each chunk of land as a node and each bridge as a connection between nodes, which we'll call an edge. We call this collection of nodes and edges a graph, and it represents in an abstract way the connections between different objects. How does this help us with our path planning problem? Well, for a continuous path, if you go into a node, you must also go out of the node. So for a continuous path, there must be an even number of edges that connect to each node. If we look at Königsberg, there's an odd number of edges that connect at each node, meaning it's impossible to find a path that crosses each bridge exactly once. A related statement is also true. If all nodes connect to an even number of edges, an Euler circuit, or a path that crosses each edge exactly once, always exists. So if you find a complicated graph like this, you can notice that each node connects to an even number of edges, and you can be sure that an Euler circuit exists. So what does that have to do with this robot? Well, that requires understanding how this robot works. This robot consists of a bunch of little roller robots that travel up and down an inflated tube. These robots represent the nodes of a graph, and the inflated tube represents the edges. For every graph where an Eulerian circuit exists, or where the number of edges at each node is even, we can form a robot by routing a single tube through a set of nodes. So now you understand how an Euler circuit relates both to crossing bridges in a city and controlling a new type of robot. I'm always surprised in mathematics how the same mathematical principles will often relate to totally different applications. Thanks, and stay tuned for more.